Here are the solutions to the Quiz 5 review. To get the details of my solution, stay tuned. In this video, we're going to look at the problem of finding unit, tangent, and standard unit normal vectors. So suppose f is a fourth degree polynomial with the following properties. F of 2 equals 3, f prime of 2 equals negative 4/7, and f double prime of 2 equals 2/3. What we're asked to do is find the unit tangent vector and the standard unit normal vector at the point where x equals 2. And we can assume that the orientation of the curve is from right to left. So that means it's going in that direction. Alright, so let's think about what all this means. So if f is a polynomial, what that means is that it's continuous and it's also differentiable, and in fact it's infinitely differentiable. You can find any derivative you want for this function. So that means it's going to be smooth, and that allows us to find the two vectors we're discussing. Okay, so what do these three facts tell us? Well, f of 2 equals 3, the original function tells us about points on the graph. So what this tells us is that the point x equals 2, y equals 3 is on the graph. And the derivative in the next line, f prime of 2 equals negative 4/7, that tells us what the slope of the function is, or the slope of the graph is, at x equals 2. At x equals 2, the slope is negative 4/7, which is negative. That means the function is decreasing. And then the second derivative tells us about the concavity. The function is, and let's see, the second derivative is positive, so it's concave up at x equals 2. So let's just draw a quick little graph of what this is going to look like near x equals 2. So the point x equals 2, y equals 3 is on the graph. Now the slope is negative 4/7, so I'm going to draw a tangent line, and let's see, it would look kind of like this maybe. That is approximately a slope of negative 4/7, so maybe it's a little bit under, but it'll do for the purposes of this example. Alright, now the function is going to be tangent to this point, tangent to this line at that point. And let's see, we also know that the graph is concave up. So if I turn the graph around so that the tangent line is horizontal, I know that it's concave up, so the graph is going to look kind of like this. Let me turn that back around. It's going to look like this. But what I'm going to do is I'm going to draw the graph like, I'm going to turn the graph so that the tangent line is horizontal, and I'm going to draw something like that. So that I'm drawing a minimum, right? Concave up. And when I turn it back around, it's going to look something like that. So in the neighborhood of x equals 2, the graph is going to look something like that. And remember that the orientation of this curve is from right to left, so that would be in that direction. Alright, so what does that tell us about the unit tangent vector at this point? Well, we know it's going to be parallel to this tangent line, and so we can even, the proper place to draw it would be to draw it so that it coincides with the tangent line. And we also know which direction it's going to be pointing in. Since the orientation of the curve is in this direction, that means if you think of the parameter and the orientation is telling you the direction of motion, we're moving in that direction, and so the tangent line would also be moving in this direction. And it would have, since it's a unit tangent vector, it would have length 1. So that's our unit tangent vector. Now what about our unit normal vector? Well, the unit normal vector at this point is going to be perpendicular, or orthogonal if you prefer that word, to the unit tangent vector. Now it can either point up and to the right, or it can point down and to the left. How do I know which way it's going to point? Well, you might remember that when we're talking about functions of a single variable, that the graph and the vectors are all in the xy plane, and that the standard unit normal vector always points toward the concave side of the graph. So in other words, it's going to point in that direction. So this is our unit tangent vector. This is our standard unit normal vector. So we've got a picture, but what we need now are components for these things. All right, so let's start with the unit tangent vector. For the unit tangent vector, we know that the slope is going to be -4/7. Now we can think of that as -4 over +7, or we can think of it as 4 over -7. And which is the right way for us to think about it? Well, let's see. Remember that when we're talking about the slope, the numerator gives us a change in y, and the denominator gives us a change in x. Well, look at what's going on here. Our unit tangent vector is pointing in this direction. So I'm going to draw a vector in that direction, more or less. I probably didn't get the direction completely correct, but it's okay. Now, in going from here to here, what is delta y? Well, it's going to be either 4 or -4. I guess I'll call that 4 because it's increasing. And then the delta x would be, well, we're going from here to here, so it's decreasing. That would be a -7. And so this tangent vector would have components x equals -7 and y equals 4. But notice I did not call it a unit tangent vector, because I don't think this thing has, in fact, I'm certain this does not have magnitude 1. The length of this vector is not 1. So what we need to do is scale this so that it has a magnitude of 1. So remember how to do that. We find a unit vector in the same direction as this. That means we need to divide by the magnitude. Right? So the unit tangent vector would be -7, 4, divided by the magnitude, which would be, well, if you square 7, that's 49, and if you square 14, that's 16. 49 and 16, I believe that's 65. And if you prefer, you can write that as -7 over root 65, comma, 4 over root 65. Okay, so now what? Well, our standard unit, our unit tangent vector, we've got. Now we need only the standard unit normal vector. Well, how do we find that? Well, first of all, we need to remember that these two things are perpendicular. These two vectors are orthogonal, so that means that the line that t lies on and the line that n lies on are perpendicular. And so this line has a slope of -4/7. Well, remember about perpendicular lines. Down here, the slope is going to be the negative reciprocal, so you need to switch the numerator and denominator, and you need to change the sign. So instead of being negative, it's now going to be positive, and it's going to be 7 over 4. So it's the negative reciprocal, change the sign, and then flip the fraction. So, what does that mean for our vector? Well, if it were pointing in this direction, the x and y components would both be negative. But it's pointing in this direction, that means the x and y components are both positive. So this is delta y over delta x, remember? And through an argument similar to what you did over here, remember this is the delta y and this is the delta x. So the vector we're going to get is 4, 7. And now we just need to normalize that, scale it so that its magnitude is 1. Well, what you're going to do is just divide by the square root of 65 again. And so the unit normal vector would be negative 4 over, positive 4 over root 65. I don't know what I was thinking. And then 7 over root 65.